Welcome back, everyone. Here we are where we left off last time. We already have our time series generator and our data is scaled. Let's go ahead and now create the model. We'll first start off with a couple of imports. We will say from TensorFlow.keras.models. We will import the sequential model that we've always been working with, and then we'll import our specific layers. From TensorFlow.keras.layers, we will import dense and LSTM. Now we're only using one feature in our time series, essentially the previous sales data. So the number of features right now is just equal to 1. And now let's create our model. We'll say model is equal to sequential. And then we're going to add in our LSTM layer. And typically you can go pretty large with the number of neurons in this LSTM layer. We'll go ahead and do 100. And then we can also play around with things like activation functions. So previously we left a default activation function. That's also something you can do. But I do want to show you that if you do want to edit the activation function for an LSTM, you can say activation and set it to something like rectified linear unit. So that's another aspect of an LSTM that you can play around with. And if you do Shift Tab here to check out the docstring, you can also do lots of other things like set initializers, regularization, etc. And we'll talk about regularization and constraints later on in the course. And what's really nice here is you can also set dropouts. Okay, so right now we're keeping things simple. This data set is actually pretty straightforward, so we don't need anything fancy to get a pretty good forecast. The thing that we do need to make sure that we get correct here, and this is something that you don't really have options for, is the input shape. The input shape should be the length of the batch by the number of features. And then after that, we also need to make sure that we add a final dense layer to have one final predictive output. And let's go ahead and just compile all this. We'll choose the optimizer to be atom. So we'll say optimizer is equal to an atom optimizer, and the loss should be for a continuous variable, since we're working with continuous sales data, and that will go ahead and be mean squared error. And then let's get our model summary, and there's our sequential model. Okay, now as I mentioned before, recurrent neural networks often take a really long time to train, and they take many epochs for training. So what would be nice here is to create an early stopping mechanism, so I can just set an arbitrarily high number of epochs and let TensorFlow do the work of figuring out when to stop training. We'll do that just as we did before by saying from TensorFlow.keras.callbacks import early stopping, and then let's create our early stop callback. And that will be early stopping, and what we're going to be monitoring here is our validation loss. And for this particular case, especially with recurrent neural networks, I would recommend just having a little more patience than the default. So recall that if we take a look at what patience actually represents, it's the number of epochs we want to wait beyond after which no improvement. So it's a number of epochs with no improvement after which training will be stopped. Recurrent neural networks can definitely be pretty noisy in the first couple of epochs, so it's probably a good idea to not have the default patience as 0, because that's very likely to end training probably a little too soon. So I will go ahead and say wait for at least 2 epochs. Okay, so we have our early stop, and now it's time to create our validation generator. Recall, since we're running fit generator, the validation set that's going to be passed in during training also needs to be a generator. So we'll say our validation generator is just as before a time series generator, except now it's on the scaled test data. So the scaled test data is both the source of our X and our Y. The length should be the same as our training set, and the batch size is going to be the same as well. Okay, so this is essentially a carbon copy of our previous time series generator, except this time we're going to be passing in this test data. That way we can then have our validation loss during training and early stop if we need to. Then the last step is to fit our generator. So we'll say fit generator, pass in generator, which is our training generator, and then we'll go ahead and choose a large number of epochs. Hopefully it doesn't need to train for that many. And then our validation data is equal to the validation generator that we just created. And then finally, we want to make sure that we don't forget to add in our callbacks, which is going to allow us to commit to an early stop here. So go ahead and run that. Make sure you don't get any typos here. And there we can see it's running. So on my computer, it took about 8 epochs of training. So I will fast forward in time until this is done training. Okay, I finished training my model. So this time it took a little further than 8. It went to 11 epochs. Let's go ahead and visualize the losses. We can do this by saying PD data frame, and then passing in model dot history dot history, and then simply say losses plot, and we can see here our loss and our validation loss. So it looks like we got quite a bit of noise, and then we went back down to our original value that was kind of our minimum here, around 8 epochs. So as I mentioned, in the beginning, the training can be quite noisy, so it's probably better to have a little more patience. Now, too much patience, and you'll probably start getting too much noise and end too late. So keep in mind, it is a bit of a balance there. Okay, so let's actually see on some test data how we performed. So to do this, what we're going to do is I'm going to copy and paste the same for loop that we created last time. So if you have any questions on this, make sure to check out the previous lecture, but we're using the exact same for loop that we used in the previous training lecture. So I'm going to go over it here, but again, the full detailed explanation is in the previous lecture. But I have my test predictions going to start off as an empty list. And then I need to figure out, well, my first training batch, what's it going to look like? It's the very last batch points from my scaled training set. Recall that the length of my batches is 12 months. So I'm going to grab what is essentially the last 12 months of my training set to predict 1 month into the future, which by definition then is the first point in my test set. So that's my first evaluation batch. Then I need to make sure to reshape it to the correct format that is expected by my recurrent neural network, because I'm passing in just one item per batch, and then it's 12 months by one Y feature. So I reshape it to that format, and then I have my current batch. Then what I'm going to do is for the entire length of my test set, in this case, I get the prediction 1 timestamp ahead. So 0 is just grabbing that number. So I predict 1 timestamp ahead. I get my current prediction. I append my current prediction to test predictions. And then what I'm going to do is this indexing right here drops the very first value in that current batch, and then I append my current prediction value, essentially moving the current batch 1 month into the future. And as we keep moving into the future, I have more and more predictions, essentially predicting off predictions. So that's what a true forecast is. Let's go ahead and run this. And again, I would recommend that you just directly get this from our notebook. It's really easy to make typos here. And then what we'll do is we have our test predictions values, but recall they're scaled. So what we need to do is inverse that transformation. So we'll say scalar inverse transform on my test predictions and set that to what I'll call my true predictions, basically my predictions at the correct scaling. So we run that, we get our test, and I'll say my predictions is equal to my true predictions. And you may get a warning here. It's basically just telling you, hey, you're overwriting tests that already exists. You can completely ignore this warning. There's actually a whole caveat linked to the documentation on this warning, but you can completely ignore it. It's totally okay. And now when we check out our test, we have our true sales data and then our predictions. Let's go ahead and see how these line up on a plot to see how far off we are. So we'll say test plot fig size is equal to 12 by 8. Go ahead and run that. And if we take a look at our predictions, they look pretty good. Granted, they're not perfect, but given the fact that at the end we're essentially forecasting off forecasts, the general seasonality trends do tend to line up. And keep in mind, this network doesn't actually have a true understanding of things like December is a holiday, so there should be a lot of clothing sales. Instead, it's learning based off the previous cycles what the trends should be. So it's kind of impressive the fact that the network is able to perform this well at all. Okay, so another thing you can experiment with is trying to use the default activation functions of LSTMs instead of setting it to a rectified linear unit and see if that improves your results. So there's lots of different options you can play with, removing or adding more neurons to the LSTM layers, etc. But let's go ahead and try to forecast into the unknown future. So what we'll do is we'll retrain on all our data, and then again we'll do our scaling, do a retraining, and then we'll do a true forecast. So right now, recall that these blue values are values that we actually know the true results for. So if we decide that, hey, this is good enough to essentially forecast values, then what will we do into the future? So we'll say forecast. Actually, before we do that, we need to actually start scaling our data. So I will say my full scalar is equal to min-max scalar, and I will scale my entire data set. We'll say my full scale data is equal to full scalar dot, and here I can fit transform to all my data since the quote-unquote forecast section doesn't really exist for me. So we'll say fit transform df. Okay, so now my data frame is fully transformed. So now I have the scaled full data. We'll use the same batch as before, say length is equal to 12. And then say generator here is equal to a time series generator. And then we'll pass in my scaled full data. Pass it in twice because it's both the source of our x and our y. The length is equal to length. And then the batch size is equal to 1. Okay, so there's our new generator. It's time to add in our model. So we create a sequential model. I can add in, assuming that I was satisfied with the model before, let's go ahead and just use the exact same one. And I'm not going to make claims here that this is the best model possible. In fact, I would encourage you to play around with it, but the results were pretty reasonable given our plot. So we'll go ahead and just say input shape is equal to length by n features. And then we'll say dense is 1, and we'll go ahead and compile this. So we'll say optimizer is equal to atom, and then say loss is equal to mean squared error. And then we'll say model fit generator is equal to generator. And now I have to choose a number of epochs. Now, a really common question I get from students at this phase is, how many epochs should I be choosing? And why can't I just do an early stop callback again when I'm forecasting into the unknown future after retraining on my entire data set? And it's a bit tricky to answer, but let's just think about what we want to do. Recall, if we come back up here, the way that early stopping works is it evaluates your validation loss. Recall that that validation generator is validating your model and evaluating your model on data that the model does not get to train on. However, by definition for this forecast, we're training on the full data set. So there is no chunk of data that we're setting aside that is fair game for evaluation because the model gets to see all the data at once. So it's a bit of a catch-22 because if you try to implement an early stopping right now by passing in some sort of validation generator, it's not going to be a fair evaluation because you'll have to actually use some portion of data that your model is being trained on. And then if you decide to actually set that data apart, then you're basically doing what we did before, which was forecasting into a known test set. And what we really want to do is take advantage now of our full data set, assuming that we're satisfied by the performance against the test set. And this is what makes time series forecasting different than typical regression models that we saw earlier, such as the regression model for pricing house data. It's the fact that we're forecasting into the unknown future, so we should be using all the data right up to the present day, which then doesn't really allow us to save anything for a test set for some sort of early stopping mechanism, which is why it's so important to essentially do that step during the testing phase. And because of that, you should be choosing your number of epochs essentially based off this chart right here. And it looks like based off this chart, we didn't have to train up to 10 epochs. We got some sort of minimum on that validation loss around 8 epochs. So that's what I'm going to go ahead and choose, 8. And again, we're not really able to initiate an early stopping here without essentially cheating. So that was the whole purpose of this phase right here. Basically, initiating the early stopping, being satisfied by our validation loss, being satisfied by the performance of the model, and then choosing that as our epochs here. Okay, so we'll go ahead and run that. Let's go ahead and fit our generator. And I'm going to fast forward in time until this is done fitting. Okay, this is now finished training for those 8 epochs. The next step that we're going to do is forecast into the actual future. I'm just going to copy and paste the loop. This is the exact same loop that we did for our test evaluation. The main thing to notice here is I essentially renamed forecast to test predictions. And really, the real change here is this periods argument. previously, we were only forecasting into the length of the test set, which happened to be 12 months. We can now theoretically forecast 1 month into the future, so 1 period into the future, 12 periods into the future, 18 periods into the future, etc. The one thing to keep in mind, however, is the longer your forecast length, the more and more noise you're going to introduce, because essentially you're forecasting off predictions. So you're basically adding in more and more predictions, and each prediction is going to carry with it a little bit of noise from the ground truth. And essentially, if you try to forecast 100 years into the future, it's going to be very, very noisy. So just keep that in mind, that there is a limitation here. And typically, your forecast length should be the exact same length as your initial test length. So it's probably a good idea that this number of periods is going to be equal to your initial batch length, because that's really what your model is designed to do. Okay, so we'll go ahead and run this. And again, we're forecasting into the unknown future. And then we're going to inverse scale our forecasting. So we'll say forecast is equal to scalar dot inverse transform on our forecast. And now we have our new forecast values. So here's our original data frame going from 1992 all the way to 2019 in October. And if we take a look now at our actual forecast, these are now the next series of values. So this is going into what is essentially 2020. Now, we don't know if these values are true or not, but that's our forecast for them. The tricky part is we want to be able to add in these values with a timestamp. So how do we actually do this? Luckily for us, Pandas has built-in tools for this exact thing. And we're going to build out a forecast index. And this is one of the main differences from our simple time series prediction on just a sine wave. So what we're going to do is we'll create that date range index by saying pd.dateRange. And then we have to choose our starting date. And the starting date should be the very next month off of this. So 1 period into the future. If you were dealing with daily data, then it would be 1 day into the future. But essentially, what should the index value for this very first point be? Well, it should be 2019 11/1. So go ahead and say 2019 11/01. So it starts at the very next month. And then how many periods are we actually going to predict for? Well, how many periods was this? We already defined it up here as 12. So we just say periods is equal to periods. So that makes that easy. And then the last parameter we need to tell Pandas is with what frequency should we be creating this date range? Because if we start at 2019 and we want to go 12 periods into the future, we have to tell Pandas, well, what is a period? Is a period 12 days into the future, 12 hours, 12 months, etc.? And we want the frequency to be a monthly start. So the string code for that is capital M, S. And if you're wondering, well, how do I actually figure out these string codes? The easiest way to do it is if you actually just Google search Pandas frequency strings. So here in a new tab, I went ahead and searched Pandas frequency strings. There is a link to the documentation, but the very first link is actually a Stack Overflow. So if you click on that, it has the link, and they're called offset aliases. So he has the link here to the official documentation. But what's nice is they actually just set out a table here. So we can see here that you can do weekly frequency, monthly end frequency, etc. We're doing month start frequency because if you notice, we're always starting here at the first of the month. So that's the 01, which means the frequency code here should be monthly start. So you'll have to determine your frequency based off this data set. So there's our forecast index. Make sure we spell that correctly. So we have our forecast index. Let's go ahead and run it. If I take a look at my forecast index now, I have these points. So it's starting at 2019 11/01, going all the way to October of 2020. Now, let's create a data frame that combines our forecast values with that forecast index by saying forecast data frame is equal to PD data frame. The data is equal to our forecast. The index is equal to that forecast index we just created. And let's go ahead and give the columns the name forecast. Forecast data frame, and there it is. So let's go ahead and plot these out. So you could plot these out separately by saying forecast data frame plot and df plot, and it will create two plots for you, one of your original sales data, and then our forecast into the future. And if you want to see these on the same plot, what you can do is you can say axes is equal to df plot, and then just say forecast DF, go ahead and plot on the same axes. And that will combine these plots together onto the same plot. And if you want to zoom in, then you simply zoom in using PLT XLim. Except this time, instead of passing in straight tick values, you can actually pass in dates. So let's go ahead and zoom in, starting from 2018, 0101 to the end of our data set, which was towards 2020. So we say comma, let's just go to the end of 2020, 1201, run that, and now we can see the zoom in. And we can see right here that the forecast actually looks pretty good. And the reason there's no link here is because this is technically two separate data frames. You could concatenate these to make them into one data frame, but then pandas wouldn't color the forecast differently from the sales data. And this does not look totally unreasonable. If you were just to show this to a normal person and say, does this forecast make sense given the previous patterns? It definitely does. It looks like pretty good. Then the question is, well, how good is this forecast? Unfortunately, there's no true way of knowing that until the 2020 months. So the only way to truly evaluate this forecast that wasn't evaluating your model on the previous test set is to just wait it out and then basically see how well you performed into 2020, which is basically the whole point of forecasting. There is no value you can truly compare this to that will be correct. All right, so that's forecasting on true time series data. Coming up next, we'll go ahead and test your new skills on an exercise. I'll see you there.